My name is Neil Daswani. I'm a security engineer here at Google, and today I'm going to be talking about how cyber criminals steal money. I'm going to be talking specifically about how cyber criminals use various types of web application vulnerabilities to steal money, and I'm going to start with simple examples, and then I'll go to more complicated examples. In the course of my talk, I may refer to many resources, presentations, reports, books, certification courses, etc. Links to those are all going to be available at my site at neildaswani.com. And at the end of the talk, I'll also be giving out a couple free copies of a security book that I published. But you'll have to answer some trivia questions to get those at the end of the talk. Before I go ahead and get started, the one additional thing that I wanted to mention is that given that this is a security talk, if you have any Google-specific questions, I'm going to ask you to hold them until the end of the talk, until we stop taping, and then you can ask those. But if you have general questions about the presentation or some of the techniques, then I'd be happy to take those either at the middle of the talk or at the end of the talk before we stop videotaping. So let me go ahead and get started. One of the major shifts that's occurred over the past 3 or 4 years is that the profile of the attackers has changed. So up until about 3 or 4 years ago, when people used to write worms and viruses, they would typically want to just make names for themselves. They would release their worms out there. It would cause lots of traffic. Some servers would come down. Some patch would get deployed, and the game would be over. But the big shift that's occurred over the past 3 or 4 years is that as more and more commerce has started taking place on the internet, and as more businesses have started making more money from that commerce activity, the bad guys want to get their share. And so their end goal is money, actual money. And so in many of the attacks that I'll talk about, in the examples that I'll present, I'll tell you how these bad guys are working to get at money. Now, the bad guys may have a set of intermediate goals that may help them get to that money. And so some of the intermediate goals, for instance, are data theft. They'll steal identity information. They'll steal credit card information. They may decide to conduct extortion. So they will launch a denial of service attack against a website at, say, 8:30 a.m., to the point that it'll take down all of that bank's servers. They will send in a ransom note to the bank. They will say, please pay us X thousands of dollars, or we're going to shut down your servers. By the way, if you check your web server logs at 8:30, you'll notice that all your web servers were down, so I'm not kidding. And so extortion's another goal. Another goal to make money is to distribute malware. Once the bad guys distribute malware, they can then do all kinds of things with the compromised machines, assemble them into botnets, and or do what they would please with those botnets. So there's a number of intermediate goals. To give you a concrete example of such a organized crime network, so I mentioned that the attacker profile has shifted from amateurs to professionals that want to make money, and in many cases those professionals are very organized. It is their full-time job to attack sites. The bad guys in some cases will hire other people as mules to transfer money from one place to the other. So it's an extensive, organized network. We're not fighting against amateurs anymore. One example of such an organized crime network is the Russian business network. If you've heard of botnets like Storm, which have compromised anywhere from 1 million to 5 million machines, depending upon who you want to believe, the real number is probably closer to 1 million, 1.5 million. They're responsible for these types of botnets. Storm, for instance, is a peer-to-peer based botnets that can be used for denial of service, key logging, pretty much whatever one would like. The bad guys will rent out the machines on those botnets. They'll say, hey, I have a botnet. I have this many machines. I'll rent them to you for X cents per day. And you give me a binary. I'll put whatever binary you give me on those machines and farm them out. Another thing that the Russian business network is alleged for is a piece of software called malware alarm. So malware alarm is this piece of software which will pop up a dialog box on your PC, and it'll say, we think your computer is infected by malware. Please click here to disinfect. Of course, if you click here to disinfect, it will infect your computer as opposed to disinfect it. And so the Russian business network is a fairly organized group. For those of you that are interested in learning more about the Russian business network, come up to me after the talk. I can tell you some fun stories. So the goals of cybercriminals have changed over the years. to give you a little bit of data about various pseudo goals and intermediate goals that the bad guys have, this is a graph that I pulled out from a web hacking incidents database report that was done by Breach Security. They basically looked at a whole bunch of organizations over the course of 2007 and what types of attacks were reported for all of 2007. And so you can see that what the bad guys were mainly trying to do is steal sensitive information, like credit card numbers, identity information. Once they steal that information, they can do various things with it. They could decide to use that sensitive information for their own gains. For instance, if they've stolen credit card numbers, they can then burn those credit card numbers onto blank mag stripes of their own and hand those out to mules, who they then tell to go to ATMs and try to do cash advances and whatnot, or use the cards at various points of sale. So that's one thing they can do with stealing sensitive information. The other thing that they could decide to do is to just sell the information on the black market. So the bad guys have a whole bunch of IRC channels as well as other ways of communicating with each other, and there's an underground economy, there's a market. So on the underground market, a credit card number might be worth, say, $10 per credit card number, and they can get bought and sold in bulk. So stealing sensitive information is one thing that the bad guys do. The next highest category of intermediate goals for the bad guys that's listed on this slide is defacement. So that's simply somebody changes what's on the front page of the website to get their own, say, political message across. Now, I should mention that this particular report queried a lot of government agencies. And so because the number of government agencies queried in this report tends to be a little bit on the high side, we said defacement is probably a little bit on the high side with regards to other databases that I've seen describing incidents. The next highest is planting malware. So once the bad guys, say, break into a website, they will put some JavaScript and or ActiveX object tags onto pages such that when good users visit those pages, visit these legitimate sites, they have a binary download to the machine and they get infected without even knowing it. So that's the next biggest category. You can imagine that if we were to look at more commercial websites as opposed to government websites, the amount of planting malware would increase and the amount of defacement would decrease, simply because if a website is highly trafficked and there's lots of users going there, the bad guys simply want to take advantage of that traffic to deploy their malware and then decide what to do with the users after that point. There's one final point I want to make about this graph, and this graph is based on incidents as opposed to vulnerabilities. So for those of you that are familiar with web application vulnerabilities, you may be aware that cross-site scripting happens to be a major problem on the internet. A lot of the vulnerabilities reported are typically cross-site scripting vulnerabilities. And I'll chat a little bit about some types of cross-site types of attacks later in the talk, but the thing to keep in mind is that those are vulnerabilities as opposed to the actual incidents. This graph shows incidents, so what the attackers are actually trying versus what, say, security researchers are trying. So this slide summarizes some things about the intermediate goals on the part of the attacker. So I've given you some high-level information about trends in this space. I'll talk a little bit more about trends, but what I'm going to do is start with a simple, concrete attack, show you how it works, and then I'm going to show you some more complicated attacks as well. So I'm going to talk about SQL injection first. Actually, let me just get a quick show of hands. How many of you are familiar with SQL injection? OK, good. More than half the room, which is great. So I'm going to go through this example relatively quickly. Basic idea is that a good user might access a website in the following way. They have a web browser. They need to authenticate themselves to a web server. They typically supply a username and password. The web server then uses that username and password to allow the user to log in. Of course, before allowing the user to log in, they need to figure out if this user is indeed authentic. So the web server might make a query to a database. The database command that gets constructed may get constructed based on the user input. So the user supplied a username. The web server needs to select the corresponding password from the database and see what the corresponding password is for the username that was entered. Of course, the bad guy is not going to enter your regular run-of-the-mill username. The bad guy is instead going to enter a username like quote, semicolon, drop table users, semicolon, hyphen, hyphen, and enter something for the password. It really doesn't matter what. But the idea is that after this input is entered and is substituted into the query, the quote will close off the string literal. The semicolon will close off the first database command. The rest of the input will make up a second database command. These hyphens will comment out the apostrophe that the web application put in. And in old databases, this actually used to execute just fine and would end up deleting all the information about all the users in the database in one shot. So this would be an example of a denial of service attack that occurs based on SQL injection. Now, these types of attacks have become so prevalent and so popular and they're so well known, there's even cute cartoons about them. I'll go ahead and let you read the cartoon. So even high schools are vulnerable to this. And if you guys have ever seen the movie War Games, in which Matthew Broderick had to open up and get the password for the computer, for the high school's database, he doesn't even need to do that anymore. He just needs to have his name be, quote, Robert, or Robert, quote, drop table students, etc. So there's all kinds of other innovative SQL injection attacks that can be done. So I'll just give you one example. For instance, when you board an airplane, right, and I've been to a couple security conferences where some of these attacks have been demoed. So when you go to the gate and you give them your boarding pass, what do they do with your boarding pass these days? The boarding pass is typically just a barcode, and they scan that barcode. Now that barcode is getting translated into a set of numbers and letters, and most likely getting fed to a SQL database. So there's no reason that you couldn't enter a couple, come up with a barcode of your own, come up with a boarding pass of your own, put in a quote, semicolon, whatever, put in all these characters, and construct a SQL injected command to upgrade yourself into first class or do worse. So SQL injection just isn't relevant to the web. It's relevant to many other types of applications, pretty much anything that uses a database on the back end. So you might think, oh, this should be pretty easy, right? The problem occurred because there was a quote and a semicolon, and I should just filter out those characters, right? That seems like the easy way to deal with this problem. Unfortunately, that's not enough. So let me go ahead and give you an example in which putting in or filtering out quotes and semicolons will not solve your problem. This is an example of imagine there's a website that allows you to buy pizzas online, and that web application may have a page which allows you to view your order history so that you could see all the pizzas that you've ordered in the past month or so. And in this screen, you might imagine that there's a pull down where I could select the month so that I can view all my pizzas for that month. And the HTML form corresponding to this form might look as follows. It has basically a select block in which there's a couple different options. Each of the options have a month and a corresponding value from 1 to 12. And when the user hits submit, that value will get transmitted to the server and will become, say, part of a SQL command that will retrieve all of the pizzas that were ordered in that month. Now, of course, the bad guy is not going to enter a number from 1 to 12. What the bad guy is going to do is enter something else. The bad guy is going to enter something like, say, 0 or 1 equals 1. So at the top, this is what a normal SQL query for getting the order history might look like. It might get the pizza, the toppings, the quantities, and the order day from the orders table for the particular user that's logged in, and the order month is the order month that comes from the form. On the other hand, if the bad guy types in 0 or 1 equals 1 for the input, what's going to happen is the order month equals 0 will evaluate to nothing, but the or 1 equals 1 will evaluate to true for every single row that the database evaluates this for. And so what will get returned is all of the pizzas that were ordered by anybody. And so what the attacker is going to get is a screen that will look like this, where it will contain the pizzas, the toppings, et cetera, for all of the pizzas that were ever ordered from that website. Now, for pizzas, this might not be such a big deal, right? But imagine if this was a medical database. Well, now you have everybody's medical records, so that's pretty darn bad. Now, at the same time, this is a talk about how do bad guys steal money. So stealing information about pizzas may not be that interesting, but stealing information about money might be much more serious. So you could imagine that the attacker could instead type in a query such as, or type in input such as 0 and 1 equals 0, union select cardholder number, expiration month, expiration year from credit cards. So what this does, the 0 and 1 equals 0 will basically evaluate to nothing, right? 1 never equals 0. None of the order months should be equal to 0. So that part of the SQL statement gives me nothing. On the other hand, what happens is the results, the nothing results, get unioned with a whole bunch of results that come from the credit cards table. Now, the key thing here is that the columns, cardholder number, expiration month, expiration year, were chosen such that they exactly match the data types of the columns in the preceding order history tables. And that's why the SQL query will work. Once the bad guy is able to do this, what the bad guy will get is a result page that looks like this. There is a pizza order table that contains people's names, credit card numbers, etc. And this is how the bad guy got all the credit card numbers. So this is pretty darn bad. Note that in that query, there were no quotes, there were no semicolons, there were no meta characters, yet the attack worked. And so how do you solve this kind of problem? Well, you need to use an approach based on whitelisting as opposed to blacklisting. When you try to filter out certain characters like quotes and semicolons, it typically doesn't work because you might forget about some characters. Every database has its own meta characters. Who knows, the next version of the database might introduce some new meta characters. And so it becomes a very hard game to fight. On top of that, you might have some users that might want to enter valid data, like, oh, quote, Brian. Why shouldn't I allow O'Brien to have a quote in his name? I want the user to have a more personal connection with my website. Why? Because of whatever technology I used to build the website, should the person not be able to use that quote? And so the right way to deal with these problems is to use an approach based on whitelisting. Anytime that you're taking input from users on a website, you want to constrain and specify what is the exact set of safe, valid values that should be allowed. And so you could imagine that if I'm accepting some kind of alphanumeric string, I might use a regular expression like this. Or if I'm accepting a month, I might use a regular expression like 0-1 to 0-9. You could, of course, write much, much better regular expressions. But the idea here is not to show you the regular expressions in particular, but to just basically make the point that you should use regular expressions to constrain the correct set of input to what you would expect it to be. And basically give the user an error, some kind of error which doesn't reveal a lot of information to the user if the input doesn't match what you might expect. Once you've come up with a set of regular expressions that properly specify the set of safe inputs, you can, in addition to checking for them in your application, you could implement them in what's called the web application firewall. So for those of you that might be familiar with Apache, you can write a whole bunch of modules or use a whole bunch of Apache modules to extend the functionality of the web server. One of the modules that you can use is a module called mod_security, and it will let you specify a whole bunch of rules for all the arguments in your web application. So that is a tool that I'd encourage you to take advantage of. Finally, I mentioned that we want to allow usernames like oh, quote, Brian. And so the way that you do that properly is you take advantage of escaping functions that your database provides you with. So the name of the escaping function will differ depending upon what database you're using. But in this particular example, you just call escape with the user input. And in some databases, like MySQL, it'll take the single quote, turn it into a double quote. And the double quote, when the database receives that in a SQL statement, will basically mean to the database, interpret this double quote as a piece of data and not as a piece of control. And that will help deal with the issue. Now, there's a number of other things that you can do as well to prevent SQL injection. One thing that I would strongly recommend is taking advantage of prepared statements and bind variables. So in this approach, what you do is for all of the queries that your application might want to do, you can come up with a query template and prepare a statement with that query template. So in this particular case, we've taken the pizza order query, and we have provided that information. And what we've done is we've put in question marks for the places in the query where I expect data, and only data, to be filled in. And once the query template is specified, you can then have separate statements that will fill in these placeholders, placeholder number 1 with the user ID, placeholder number 2 with the parameter corresponding to the month. And the idea here is that when the database driver executes this, when the database looks at this, it will always interpret this information as data. It will not allow the structure of the query to change. And so you could imagine that what you could also do is create just one file in your application or keep all of your queries in separate places such that in your regular code, you should never really have SQL. And that will help you from a code auditability standpoint to make sure that you don't have these types of SQL injection errors. So I highly encourage the use of prepared statements and bind variables to deal with SQL injection. So I talked a little bit about mod security. Mod security is a type of a web application firewall. And so the idea here is that without a WAF, when the user makes a connection to your web server, the connection is pretty much directly to the web server. There's nothing that can really intermediate the user's request. If you do use a WAF that's either linked into the web server or that's sitting in front of the web server, the idea is that when the user input comes in, it can basically run all the user input through various regular expressions and check for invalid types of input. So that's how mod security works. Except mod security is actually linked in the web server as opposed to a separate box. There are also web application firewalls that sit in front of a box, but the last thing you need is another security appliance to manage. And so while that is one option, there are others as well that can be based on software. To give you an example, another example for how to use web application firewalls to prevent some types of attacks like SQL injection, you can imagine that there's going to be a whole bunch of rules, and there's a whole bunch of public rules available. So especially if you're using Apache or you're using a public, that type of a website, what you could do is take advantage of rules that are available. And this particular rule is optimized. It's a whole bunch of regular expressions compiled into one, but you can get the idea that it looks for various parameters in the HTTP request and looks for certain scary strings like table, like objects, like the word password, etc. And so the web application firewall can be used to provide you defense in depth. So the idea is that you should absolutely try to write your code as perfectly as possible so that it doesn't have vulnerabilities, but you just never know. And so the web application firewall can provide defense in depth. If there's some class of attack that you didn't have in mind when you built your application, the web app firewall might be able to help protect you. So what else can you do to mitigate SQL injection? Well, one thing you can do is you can limit privileges. If your database doesn't need to change data, then there's no reason that the user account that the web server is logged into the database with or the web app server should belong to the database with. There's no reason it should have those right privileges. But as you can imagine, just reading data can also be pretty bad. You can harden your database server, harden your host to OS. Some databases like Microsoft SQL Server ship by default with a whole bunch of functionality turned on, so that I could write SQL commands that could be used to initiate outbound network connections or emails. And you definitely want to shut all of that functionality off. There is a lot more to learn about SQL injection. For instance, there's attacks like second-order SQL injection, where the bad guy takes advantage of data that's already been sanitized and is in the database, and does a command to re-inject that into a query and use it to their advantage. So another type of attack is blind SQL injection. You notice in some of the attacks that I demoed, the bad guy needs to know a little something about the structure of the database. And so blind SQL injection is a technique that can be used to reverse engineer information about the schema of the database. If you're interested more in that, I suggest chapter 8 of my book or the web. There's a lot of good information out there. So that is attack type number 1, SQL injection. That's one of the simpler attacks. Can I answer any questions about SQL injection before I move on to the second type of attack that I'm going to talk about, cross-site request forgery? No questions about SQL injection. OK, I'm going to move on to talk about cross-site request forgery. So this is another attack which can be leveraged by the bad guys to steal dough. And how is the bad guy going to do that? Well, I'm going to show you by way of example. Let's assume that we have 2 sites. One site called bank.com, which is a legitimate site that has an online banking application. And let's assume that a user logs into that online banking application and is authenticated with a cookie. So the idea is that the user goes to the front page of bank.com, provides a username and password. Once the user is logged in with that username and password, the the user's browser is given a cookie, and on subsequent HTTP requests, the user's browser supplies that cookie to the bank's web server. That's what authenticates the user. So let's assume that's how bank.com works. Now let's say that the user is logged into bank.com, and the user happens to get lured to some evil site called evil.org. The idea here is that a user might receive an email, and there might be a link in it. They might end up clicking on it. There's many, many different ways to lure the bad guy to evil.org. But let's say that there is this site called evil.org, and it has some malicious web pages. Let's look at how evil.org can effectively steal money right out of the user's bank account. So how this attack is going to work is Alice, our good guy, or good girl in this case, is going to go to bank.com and request the login form. The login form is going to have a form for a username and password. The user, Alice, is going to fill out that form and provide bank.com with the username and password. The username and password gets transmitted to bank.com. Let's say that particular script is called auth. The username happens to be victim. The password happens to be whatever. And bank.com checks that information in their backend database. It checks out, and so bank.com sends Alice a cookie. Here's your session ID. You can give me back this identifier to authenticate yourself. Now, you can imagine that in a normal world, in a good world, Alice might then, once she's logged into the bank's web server, she might click on a link saying, I want to view my balance. So what happens when Alice clicks on the view balance link? Well, a view balance script might get called. Of course, because this cookie came from bank.com and Alice is making another request to bank.com, the browser provides bank.com the cookie. And so bank.com says, oh, OK, I know, this is Alice. She just logged in. Let me go ahead and give her her bank balance, because she's an authentic user. So it says your balance is $25,000. Now, of course, let's look at what happens when Alice gets lured to a evil.org site in the middle of this interaction. So as before, Alice makes a connection to bank.com. She requests the login script. She authenticates herself with a username and password. She's given a cookie. Now, what's going to happen at this point is, let's say that while she's logged into bank.com in one window, she opens up another window and is reading her email and happens to click on some link, or comes up on some drive-by download page or whatever, and is served a page by evil.org. Well, what evil.org can do is serve her a web page that has some HTML on it. So let's say that Alice requests evil.html. And on evil.html is the following tag. And I've simplified this from a technical standpoint just to make the clarity of the explanation a little bit better. But you can use JavaScript or whatever else. But the idea is that there's this image source tag that has a URL that says, go make a request to bank.com. And so it specifically says, hey, go ahead and make this request to this paybill script at bank.com to go ahead and get this quote-unquote image. And by the way, supply these parameters. The parameters are the attacker's address and the amount, in this case, $10,000. And so what does Alice's trusty browser do? Well, Alice's browser wants to do a good job for Alice, and so it makes a request to bank.com. And it calls the paybill script as was requested. It passes the parameters as were requested. And oh, by the way, since the browser was already logged into bank.com, it sends the bank.com cookie to bank.com. So bank.com gets this request from Alice saying that she should pay a bill to 123 Evil Street in the amount of $10,000 and looks at the cookie. The cookie is completely legitimate. So what does bank.com do? Bank.com goes ahead and issues the payment. Right? Now, of course, if you're the attacker, you want to do a bunch of things to make sure that Alice didn't see that. So you open up, the way you do this is you send back this kind of script in a zero-size iframe so that Alice didn't really see anything. The other thing is that from an attacker standpoint, this would generate lots of forensic information, right? The evil guy doesn't want to go ahead and give exactly his address to the bank because at some point Alice is going to complain, is going to go back to the bank, say, I didn't withdraw this $10,000. So this is where hiring mules comes in. So if you've ever seen these websites where what the bad guys do is they'll put up a website that looks like it's a legitimate company. The legitimate company will have a bunch of job descriptions on it. One of the job descriptions will say, oh, we're looking for an assistant or a work-from-home job at some point. And that will have a whole bunch of qualifications listed for this person, like they should know how to type at a certain speed, they should know how to use the internet. And one of the interesting job qualifications is that they should have access to an internet bank account or a mail address. And so what the bad guy does is hires a bunch of mules and puts the mule's address here and gets the $10,000 sent to the mule, and then the mule is instructed as part of their job to keep 10% of it and then transfer the rest of it to the attacker's bank account. So that's how the bad guys turn cross-site request forgery attacks, web-based cross-site request forgery vulnerabilities into ways to steal money. Did that make sense? Any questions? OK. So that's how to use cross-site request forgery to steal money. How many of you have heard of an attack called drive-by farming? OK, very few of you. OK, how many of you, when you got your home router, changed your default username and password? Why isn't it everybody? So the issue here is that because of this cross-site request forgery vulnerability, it's possible for the attackers to completely take over all of a user's internet browsing simply because of the fact that they didn't change that password. So most home routers will have a web-based interface which lets you administer the router. And what the bad guys do is they know that approximately 50% of home users use a broadband router and they don't change the default username and password. So what the bad guy can do is take advantage of cross-site request forgery to mount an attack against the home router where what they do is they change the user's DNS settings. Right? So basically, I include this image source and other type of JavaScript that will make a request to the router at 192.168.0.1 or whatever predictable address is. The attacker can try a whole bunch of them. And it will basically send a message to the user's router saying, please change the user's DNS settings to use the attacker's DNS server. Once that's done, even if the user types in www.sitename.com, it will get resolved to the attacker's IP address, and the attacker can put up a website that looks exactly the same. Once the user enters their login credentials, he just fishes those out. And so this slide has a whole bunch of details about how you actually do this, but you could imagine that there's other applications here as well. So farming is an application where I change the user's DNS settings, but there's other applications. I couldn't, for instance, build a port scanner using this kind of technique, where if I'm trying to get at people behind corporate intranet sites, I know they may have, say, a whole bunch of 10 dot addresses. So what I do is I have a whole bunch of these tags. I have a whole bunch of 10 dot or 192.168 internal IP addresses, and I can basically, using handlers like onError, figure out exactly when my successful request did get sent and did not get sent. And so there's a lot of applications here for cross-site request forgery. Drive-by farming is one. It's some good work that was done by Sid Stam, a PhD student who interned with me last year. Marcus Jacobson and Zulia Ramzan were also on this paper. So I've told you about cross-site request forgery. I've told you how you can use it to steal bank accounts, how you can use it to take over the user's DNS. You can use it to do corporate espionage. How do you stop it? Well, there's a variety of techniques, right? Earlier, I said that the request looks completely authentic to bank.com, and it does. But for those of you that are familiar with HTTP, you know that there is a referrer header that gets sent along with the browser. And so one question that you may have in your mind is that, can I look at what the referrer is? You can imagine that when I try to view balance or pay bill and the user is only on the bank's website, the referrer will also be the bank's website. But if it's evil.org's site that's sending back evil.html and making a request to bank.com, the referrer should in fact be evil.org's evil.html file. So So it's a good idea. The problem is that lots of users may use HTTP proxies for whatever reason. They may use anonymizing proxies. You might want to browse the web remotely. And so refers don't always necessarily get sent. So if you're looking at using refers to be a completely fail-safe mechanism to deal with cross-site request forgery, you're not going to get very far. On the other hand, there's some good work that's come out of Professor John Mitchell's research group at Stanford, and I believe there's similar research reports elsewhere, where what you could do is look at all of your aggregate traffic on a site and look at what percentage of that traffic doesn't have the refer fields. Is that normal? Is that not? For those requests that I am getting, am I getting lots of requests to the pay bill script without a refer field? Well, that's a bad sign. And by the way, if I do see some pages that I don't expect, well, that might be a sign that there is some kind of cross-site request forgery going on. So inspecting refer headers won't give you a fail-safe defense, but it may give you some indication. It may allow you to detect that the problem is happening, even if it doesn't allow you to prevent it. You can attempt to use a web application firewall, but the request pretty much looked legitimate to bank.com, so it's going to look legitimate to the web application firewall. Now, at the same time, I mentioned that you could look at distributions of traffic, and the web application firewall may help you do that, except for the fact that most firewalls, web application firewall, for instance, mod security, doesn't support that level of functionality. So that's another potential defense. Even better defenses are validation via a user-provided secret. So the idea here is that whenever the user is going to do some sensitive operation like paying a bill, what you want them to do is you might want them to enter their password again. Right? The reason that the cross-site request forgery attack worked was because the bad guy was able to make a write request and didn't have to know any information about the user because of the fact that the cookie automatically got sent and automatically authenticated the user. On the other hand, if in the HTTP request to pay the bill, you require that the user provides their password again, then of course the hope is that the attacker does not know the user's password and will not be able to specify that secret in order to do the transaction. And of course, if the attacker does have the user's password, they can do a whole bunch of other bad things anyhow. So asking the user to type in their password or some other user-provided secret again, a PIN or whatever, is a good way to mitigate cross-site request forgery attacks. A fourth way that you can deal with cross-site request forgery is validation via an action token. So what you can do is take some secret that should only be known to the server, combine it together with things like the user's session ID, and use a cryptographic primitive like an HMAC to generate some new piece of data, some new signature that gets sent out with every page that you serve the user, and basically put that in all forms. And so the idea is that the bad guy won't know what action token to provide when doing the sensitive operation. And I've kind of glossed through the details of how to do that here, but if you're interested in all the details, Christoph Kern, my co-author, wrote up a great section on how to do this in the cross-site, cross-domain attacks section of my book, chapter 10. And I'll be giving out some free copies. And for those of you at Google, we actually have that book available internally if you're interested in a copy. So that's how you can prevent and detect cross-site request forgery attacks. Can I take any questions about cross-site request forgery before I move on to cross-site script inclusion? No, clear, good. So the next attack that I'm going to talk about is cross-site script inclusion. It's similar to cross-site scripting, except it takes advantage of the fact that lots of web applications are now using Web 2.0 AJAX type technology. And so I'll tell you a little bit about some of the downsides and some of the new attacks that can happen if you're not careful about how you use AJAX objects like XML HTTP request. And or if you use a framework, some kind of framework to automate the development of your Web 2.0 application like XAJAX or SAJAX or whatnot, you should have an idea of what the limitations of that framework are. So let me go ahead and talk about cross-site script inclusion. As you all know, when you're building a web application, you can have script tags, and you may put the JavaScript directly in the HTML file, but you may also decide to factor out your JavaScript into a separate file. And then you can use a script tag followed by a source attribute to include that tag. And so this is called static script inclusion, and it allows you to share code, right, between various pages on your website. It also allows you to source JavaScript from other websites. So there's a lot of advantages that come with that, but it could be dangerous. For instance, if you decide to source in a third-party JavaScript file, then they could do lots of bad things to your web page without you even knowing it. So that's static script inclusion. There's also dynamic script inclusion. And maybe what I think I should do is just go into an example. But you can imagine that when I make a request to an HTTP server, that HTTP server, in addition to sending back HTML, can also send back JavaScript. And it can send back different JavaScript depending upon what's in the request. And that's an example of dynamic script inclusion. So let me make things a bit more concrete and then show you what can go wrong. So in an example where we have static script inclusion, you can have a web page, and I might be showing the user their mail, and I might like their page with their mail to have a cool menu on it. And so I can go ahead and source in a menu.js JavaScript file, which will go ahead and do all the right things and render that menu. And so static script inclusion itself is not a bad thing, so long as you trust menusite.com. Now, there's also dynamic script inclusion. So you can imagine I might be building a banking website, and I want the user interface to have very low latency, and I don't want to have to re-render the whole page to, say, just show the user their balance. And so I might build a page like this, where there's some JavaScript on view balance. So what it can do is make a request to the server to get the user's balance, and then call a render data function to render that in place without having to reload the entire web page. So in this script, the first line will go ahead and create a new XML HTTP request object. I'm assuming everyone here is familiar with XHR. And what you can do then is you can set a handler so that when this XML HTTP request is complete, this handler will get called. What this particular handler does is it just takes the response that it gets from the server. The server will basically give back a JavaScript function call, and it'll go ahead and call eval on it. So it'll go ahead and execute that function call. Once the state change handler is set, this code then opens up HTTP post request to this particular URL. It says, go to bank.com, call this getData script. It gets back the data in JSON format, which is a popular way of giving back attribute value pairs. And it says that, oh, when you're finished with getting this data back from bank.com, you should go ahead and call render data. Or it's basically telling the server that, give me a render data call as your result. And then it'll go ahead and send the HTTP request. And of course, also in this code will probably be the code of the function for render data, which will find the appropriate DOM object in the web page in which to stick the balance once it arrives back from the server. So this is what things look like in this particular application. And in a normal world, we wouldn't have problems. But of course, we live in the real world, so we're going to have problems. So let me demonstrate exactly what happens with regards to how this code works, and then show you what can go wrong. So Alice may decide to log into bank.com. She goes and gets the regular login script. She gets back a cookie. She might click view balance. And when she clicks view balance, bank.com gives back viewbalance.html. And when Alice's browser gets that code back, it starts evaluating the JavaScript in it. So it goes ahead and makes the post request that was in the JavaScript. It passes the appropriate callback parameter. And so bank.com gets the request. Bank.com gets the cookie. This is Alice. I'm going to go ahead and send back her bank balance information, except that bank.com is a cool Web 2.0 application now. And so it sends back this data in the form of a JavaScript callback with some JSON that has an attribute value pair for the account number and an attribute value pair for the balance. And that data goes back to the browser. The browser says, oh, OK, I'm just going to go ahead and eval this. I'm going to call render data with these JSON parameters to render the data on the web page. And so things should work just fine, unless we have an attacker in the loop. What the attacker is going to do is similar to what happened with the cross-site request forgery attack, what's going to happen here is the user might get lured to evil.org while logged into the bank.com website, and the evil.html that the attacker is going to send back is going to be a little bit different in this case. In this case, as in the previous case, the bank.com or evil.org has studied bank.com's website, and so it sends back some JavaScript which takes advantage of this render data function. So evil.org knows that there's a render data function being used, and the evil site provides its own implementation of a render data function. So this render data function, instead of rendering the data on any kind of web page, will call another JavaScript function which will send the arguments passed to this function off to evil.org. Of course, because this page comes from the evil.org domain, it can go ahead and send data back to that domain as per the same origin policy. So that's one part of the script. The other part of the script that is in evil.html that gets sent back is basically a tag which says, go ahead and call that getData script on the bank.com website, and of course, call back the render data function. So the user's browser gets evil.html and wants to faithfully render evil.html for the user, and makes the post request to the website, passes the appropriate parameter, of course, because the user is logged into bank.com, provides the session ID in the cookie. Bank.com successfully authenticates Alice. Bank.com sends back the render data script and the JSON parameters containing the account number and the balance just as before, except now what happens is that because this is being rendered on evil.html, it goes ahead and calls the render data function in evil.html, which basically says, send these parameters off to evil.org. And so the attacker gets the account number and gets the balance. Bad news. And then the attacker can do whatever the attacker would like with this information. So this is yet another example of cross-domain security problem, and how the attacker can, in this case, steal the account number as well as find out what's in the balance, and then sell that information or do whatever we would like. So what happened in cross-site script inclusion is the malicious website requested dynamic JavaScript. The browser authentication cookies would be sent because the user is already logged into bank.com. The JSON fragment returned by the server is accessible, and it's going to be sent back to the malicious site. And the bad guy simply redefined a callback method to make this happen. So that's cross-site script inclusion. So at this point, I hope I've scared everyone a little bit with all the technical details of how things can go wrong. Let me talk about a couple trends. So I'm going to cite a couple research reports. One is by Symantec, and in Symantec's latest Internet Security Threat Report reported that 58 of all vulnerabilities in the second half of 2007 affected web applications. So the bad guys are shifting more and more to attacking web applications as opposed to, say, attacking open DCOM vulnerabilities on your PC. One other interesting thing that was mentioned in this Symantec report is that the bad guys can go ahead and look at large popular sites that have vulnerabilities, and it sometimes makes sense for them to put a lot of effort exploiting those vulnerabilities on large traffic sites instead of going for smaller sites. So that's a particular trend that was highlighted in the Symantec report. Now, about 2 weeks ago, there were also attacks where what the bad guys did is they took advantage of kind of the opposite. They attacked a whole bunch of small websites. So what they did is they used various search engines to look for IIS servers, Microsoft's Internet Information Servers, and look for SQL injection vulnerabilities and applications that would use that database. So basically, they would get back a whole bunch of search results, and they would know exactly what servers to exploit. So this can also go the other way around, where the bad guys can attack lots of small sites very quickly. So on one hand, large sites are this is an issue for large sites. On the other hand, it's an issue for small sites. It's basically an issue for every site. Another statistic is that Sophos noticed that 80% of sites hosting malware are legitimate sites that have been hacked. So many of the small websites that I just mentioned would all render content to their users that came from the database. So what the bad guys did is they used techniques like SQL injection to inject malicious JavaScript and or ActiveX type objects that once users would end up on those web pages, they would get infected by malware. So that speaks to this statistic. So users are not safe necessarily browsing legitimate sites. We basically need a lot more AV technology on this front. We need websites to get better about their server-side security. And statistics from Symantec and Sophos are good. I'm sometimes skeptical about statistics that come from market research firms, but even Gartner says that today over 70% of attacks are against a company's website or web applications on their site. So things could be a heck of a lot better. And given this knowledge and how to prevent these kinds of attacks, we can all help make things a lot better. To show you one more graph, let me show you another graph that came from this web hacking incidents report. It basically shows that with regards to actual incidents, 12% of the attacks are due to cross-site scripting, 20% are due to SQL injection, etc. So actually, I should mention one more thing about this pie chart. There's an organization called the OWASP, the Open Web Application Security Project, and they basically every year publish a top 10 web vulnerabilities. So what breach security did in this case was they took those top 10 web vulnerabilities, plotted them against the incidents, and found that the number one web vulnerability, cross-site scripting, actually was only 12% of the attacks, whereas SQL injection, while it was number 2, actually accounted for more incidents. So there's more cross-site scripting vulnerabilities, but there's more SQL injection incidents. So let's see. I'm going to summarize by telling you where you can learn more. I'm going to tell you about some courses, certification programs, etc. This list is not comprehensive by any means. You can learn more about security pretty much at every university. A lot of the good universities, in addition to having things like cryptography courses, are now introducing system security courses. So CS 155 at Stanford, W4187 at Columbia, CS 161 at Berkeley. There is a much more comprehensive list at Avi Rubin's website. So you can check that out. There's also, for those of you that have full-time jobs and can't necessarily afford to take things over the course of a semester, there's an advanced security certification program at Stanford that can be taken either online or on campus over the course of a week, where there's 3 core courses, 3 electives. And one of the interesting things about it is, in addition to just providing lectures about all these attacks and telling you how to abstractly prevent them, what we do, and I have to, in the interest of full disclaimer, mention that I helped Stanford with this program. Basically what we do is we put people in labs and we have them actually construct the attacks under some test websites that we constructed and then write the actual defenses. So that is useful, and we do that on campus. Of course, you can do that in a lab where you're kind of isolated from the real internet, and you make sure that you don't end up impacting real sites. We also took all of that all of the software that we're running in the lab, and we put them on VMware images. So even if you need to take the courses online, you can go ahead and benefit from those labs, even if you take the courses online. This is the URL. So let's see. So there's a lot more information. This is the URL to go to. Actually, this should be scpd.stanford.edu/advanced security. The next course is coming up in July, so keep an eye out for it. There's other security certification programs available. There's a certification called the CISSP, the Certified Information Security Professional. It's much more broad. It focuses on various aspects of security beyond just software security. It focuses on physical security, telecom security, etc. There's also a new certification that's come out from a group called SANS, called the Secure Software Programmer Assessment. It's basically, both of these are actual multiple choice tests, so you'll learn a lot by preparing for them. There's also lots of books. There's my book, Foundations of Security, What Every Programmer Needs to Know. I'll give out some copies. I'll do some trivia questions in just a second. There's also a lot of other good books. I'd recommend Ross Anderson's Security Engineering. It's actually available for free online. Just enter this into Google or your favorite search engine. I also highly recommend Gary McGraw's Building Secure Software book and Vega and Messer's Secure Programming Cookbook books. Let's see, there's also a website that we've helped make available called code.google.com/edu. If you need to teach a security course, you can just download materials off of this site and there's slides, there's programming assignments. So if you're responsible for teaching security to other folks, this is a resource that you could take away for free. There's also free slides corresponding to every chapter in my book at learnsecurity.com/ntk. And let's see, so I think that concludes all the information that I wanted to tell you. The key point here is that software security is every engineer's problem. It's not as if there's some group of magical security engineers that are going to take care of securing your application after it gets developed. It really needs to be every engineer's job. And I mentioned a various set of resources. In addition to my website, neildeswani.com, you can also go to learnsecurity.com. My contact information is there. So I hope that you guys have learned at least one thing new. I'd be happy to take any questions at this point. OK, thanks for your time.